right, so chapter 6 problems. Okay, this says two large rectangular aluminum plates of area 150 centimeters square. 150 centimeters square is roughly the size of a sheet of paper. Okay. Face each other with a separation of 3 millimeters between them. Okay. In one of the next chapters, you'll see this is a parallel plate capacitor. Okay. And so let me go ahead and show you one of these guys in preparation for the next chapter, or probably a couple of chapters down the road. What's going on? All right, so this is what is called a parallel plate capacitor. These are two pieces of metals, okay? And okay, so right now we've this thing is connected to a battery, except that this battery has 0 volts. Okay, so let's do this. I'm going to. Okay, did you guys see what happened? What happened was physically what happened was electrons moved from the battery to here. These electrons repelled these electrons, which came over to the positive end. Okay. Now this thing is charged. Okay, this positive plate is charged, the negative plate is charged. Okay, what do the plates want to do? I'm sorry? They're opposite charges. They want to attract each other. Yeah. Okay. And you know the electrostatic force is large. So to hold them apart, it's like a stretched spring. So there's energy stored in there. Okay. So when you charge a capacitor, what you do is you transfer energy from that was stored in the battery to here. What do you think is the point of that? The battery had the energy. Why did you transfer it here?
Now you have mechanical energy?
No, this is electrostatic energy. Go ahead.
You release it really quickly.
There you go. That's the point. Okay. This guy, a capacitor, if you want, he can release the energy in the billionth of a second. This guy takes forever. How fast can you run down a battery? Takes at least a couple of 3 hours. Okay. This guy can release him in a heartbeat. Okay, so let's charge this guy. And you see, so that's one of the things you can do. Okay. Your flash bulb camera, that's the circuit. Okay. So when your camera is blinking orange, it's charging the capacitor. Once the capacitor is charged, the light goes green and you can take a picture. Okay. And so this is what we'll study. What did the flash camera do for you? What's that? It turned night into day, and you could take a picture. It did it for a millisecond, but that was good enough. Okay? All right, so a capacitor, what it can do is, like our friend there said, it can release the energy very fast. So that's, okay. So, all right, so these are, and I'm not going to derive this. Okay, so here are two aluminum plates. Like I said, each of these sheets is about the size of the paper that you have. Okay, and you put 20. Okay, I guess that should be nanocoulomb and minus 20 nanocoulomb. Now you put the charge on the conductors, and you learned in the last chapter, when you put charge on a conductor, where does it reside?
On the surface?
On the surface. So it can't reside there, okay? All the charge goes on the surface. And how does the charge distribute? What is the goal of the charge?
Can we get as far apart from each other as they can?
The goal is to have E equal to 0 inside the metal, okay? Because if E is not 0, then there are free electrons that can move around and they can rearrange till when the electric field goes to 0. And how fast will this happen? Within a trillionth of a second. Okay, so it turns out that, okay, so this is a metal, this is a metal. You want electric field 0 in these two guys. And so it ends up happening that the charges are on the surface facing each other. There's no charge everywhere else. And this configuration will ensure that the electric field is 0. All right, and it turns out that, so you can show this using Gauss's law, but this is not part of the problem. This electric field is equal to sigma by epsilon naught. Okay, sigma is the charge density on each plate. Okay. All right, so all that to just set up the problem. Okay, now let's see what the problem is asking. So two large rectangular aluminum plates of area 150 centimeters square face each other with a separation of 3 millimeters. Okay, 3 millimeters is just that much. Okay, so imagine two aluminum sheets, and the 3 millimeters is a tiny gap. The plates are charged with equal amount. The charges on the plate face each other. Find the flux through a circle of radius 3 centimeters between the plates when the normal to the circle makes an angle of 5 degrees with the perpendicular to the when the normal to the circle makes with the line perpendicular to the plates. Okay. All right, so what you want is, this is the plate, and there is the area vector, and this angle is 5 degrees. Okay? And they want you to find the flux. Well, the flux denoted by phi subscript E, telling you that it's an electric flux, is the electric field dotted with A. What does the area vector mean? The magnitude of the area vector is the magnitude of the area, and the direction is perpendicular to the area. Okay? So this is equal to E dot area of the plate, not plate. Okay, I'll just leave it as that. A times cosine theta. Okay, E is sigma by epsilon naught. A cosine theta. All right, well, let's find sigma. Sigma is charge on the plate divided by the area of the plate. This area is different than this area. This area is that area, and the area of the plate is this area. Okay, okay, so there's the electric flux. Area cosine theta. Okay. Now we'll put all the values in and calculate the flux. Okay, the charge was 20 nanocoulombs. The area of that plate is pi r square, radius of 3 centimeters. Three centimeters is 10 minus 2 meters square. Cosine phi. Epsilon naught is 8.85 into 10 minus 12. It's the permittivity of free space. You guys can look up the And its units are newtons, coulomb square, meter square. And area of the plate is 150 centimeter square. Centimeter is square is 10 minus 4 meters square. Okay. Okay, so we got everything. Now let's take care of powers of 10 first. This is 10 minus 12. That makes it 10 to the 3. That's 10 to the 4. That cancels that. So you have 10 to the 3 left. Okay. So the flux is 10 to the 3. And flux is, what are the units for flux? It's the units of electric field times area. Okay. And units of electric field are Newton per coulomb times meter square. Okay. So those are the units for flux. And that's just 20 times pi into 9 into cosine 5 divided by 8.85 into 150. All right, so let's do this. Okay, so that is the flux through that area. Yeah, the electric flux through the area. That tells you how many sort of lines are going through that area, loosely speaking. Yeah. A vector field, what does a vector field mean? A vector field means this is a vector field. Okay. So now tell me, what does it mean?
Three-dimensional shape of a function.
So what this is saying is, at every location you're associating a vector. Okay, you're calculating a vector. So really, now you would probably understand this better. I, E, Y, X, Y, Z, J plus E, Z, X, Y, Z. Okay. So you're given a function for the X component of the vector, function for the Y component, function for the Z component. So given this guy, you can calculate a vector at every location. Okay, so this is a vector field. Okay. Just like a cornfield, on every point on the land, you can find a corn stalk. Okay? So vector field is at every point, spatial point, you'll find a vector. Okay? So this is a vector field. There's the equation. There's the function. See, this vector field has only z components. So all the vectors are pointing in the z direction. Okay? So here's a vector field. Find the flux of the vector field through a rectangle in the xy plane between x equal to a and b and y equal to c and d. All right, so but let's first draw the okay, and this is a and b and c and d. Okay, so this is the area. And the vector field is pointing in that direction, in the z direction. and do the same. Okay, so we'll just do part A. Part B, okay, we'll do both. Okay, so part A, they're asking you find the flux of the vector field through a rectangle in the xy plane. In the xy plane, this is a rectangle in the. So you want to find how many lines are going through this area. Okay, and the flux in terms of the integral is that. Okay, now what is this area? We're going to do this area. There's dA. Okay, the dA is the area is, I should really draw a rectangle, dx, dy, and what direction is the vector pointing, the area vector pointing in?
Z.
Z direction. So z hat. All right, so this flux is alpha x squared plus y squared z hat dx dy z hat. So it's a double integral, and z hat dot z hat is 1. So I'm going to erase this. Is equal to, and x goes from A to B, y goes from C to D, alpha x squared plus y squared dx dy. So that's the flux. Yep. And this integral is a little messy, so they don't ask you to do the integral. Okay. So that tells you how many of those vector field lines are going through that area. That's what it tells you. Okay, part B says do the same through a rectangle in the YZ plane. Here's the YZ plane. So here's the YZ plane. The area vector will be in this direction, and the vector field is in that direction. So for the YZ plane, again, the vector field dotted with the area vector. What do you think this is? See, this vector is pointing in the z direction. This vector is pointing in the x direction. So that dot product will be 0. Did you guys understand that? So that dot product is 0. Consider the uniform electric field there. What is the electric? So this is that's the electric field everywhere. Okay, so that's a uniform electric field. It's a vector field. It's just that the vector field is pointing in the same direction at every location. What is the electric flux through a circular area of radius 2 meters that lies in the xy plane? There's the area vector. And what is the area vector equal to? It's a circular area of radius 2 meters, pi r square z hat. That's the area vector. Okay. And the flux, electric flux, is E dot area. Okay. So 4j plus 3k into 10 to the power 3 dotted with pi r square. They're using k, so we'll use k. K. Only this survives. J dot k is 0. So this is equal to 3 pi r square into 10 to the power 3 Newton per Coulomb meter square. Okay. And R is 2 meters, so that's 4 times 3, 12. 12 pi into 10 to the power 3 Newton per Coulomb meter square. Okay, so that's the flux. Now, if this represented, instead of an electric field, the velocity of a river flowing, this would give you the number of gallons moving through that area per second. Okay, that would give you the flow rate. Okay, this problem says the electric flux through a cubical box 8 centimeters on a side is that. Okay, what does Gauss's law say? Gauss's law says the flux through an enclosed surface is equal to the charge inside the surface divided by epsilon naught. So in this problem, they tell you the electric flux through a cubical box is that. That's a positive flux. What does that mean? If this guy is positive, the charge inside is positive. If the flux going through an enclosed surface is negative, then the charge inside is negative. And what does positive flux mean? So here's an enclosed surface. Positive flux means the lines are going outside. And negative flux means, negative net flux means lines are coming in. And you have negative charges doing that and positive charges doing it. Okay. So the total charge enclosed, charge inside is epsilon naught times the flux, and epsilon naught is 8.85 into 10 to the minus 12 Newton meter square by Coulomb square. And the flux is 1.2 into 10 to the 3 and the unit for charge should work out to be coulombs. All right, so I got this, the units for this messed up. It's Coulomb square. I got them inverted. Coulomb square, Newton meter square. Okay. All right, so where were we? Coulomb square, Newton meter square. And so this is 10 to the power minus 9 coulombs. So the charge inside that surface is 10 nanocoulombs. Yep. So it's some enclosed surface. They give you the net flux through it. The flux is that, and the charge inside is positive, and that's the charge. Anybody remember the charge of an electron or a proton?
13.
It's 1.6 times 10 to the minus 19. Okay, so this is 10 to the minus 8. That means it's about 100 billion electrons. Okay, so that's what's inside. Okay, this problem says a total charge Q is distributed uniformly throughout a spherical shell of inner radius R1 and inner and outer radii R1 and R2 respectively. Show that the electric field due to the charge is this for those regions. Okay, so let me draw this guy first. So this is R1 and this is R2. Okay, so this is a styrofoam shell, so to speak, because you have to have an insulator to distribute charge. Okay, what will happen if this was a piece of metal? What would happen if I put a bunch of charges like that?
Wouldn't they go to the outside?
Yep, so very good. So they would go all to the outer surface. Okay, so if they stay here, that means they're insulators. It's an insulator, and styrofoam is an insulator. Okay, what they want you to show is for R less than R1. So in this region, they want you to show that electric field is 0. In this region, the electric field is that for R between R1 and R2. And for R greater than R2, for this region, they want you to show that the electric field is that. Anything special about this? Do you notice? Okay, don't look up your notes. For a point charge, the electric field is, at this distance, is KQ over R squared. By the way, this guy is 1 over 4 pi epsilon naught is K. Okay, so this is equal to so the field due to a point charge at this point is that. What does this look like?
Okay.
Exactly the same. Okay, so once you're outside the sphere, this is behaving like a point charge. So from here, by measuring the electric field, you don't know if the charge is uniformly distributed over a shell, a sphere, or is it a point charge. Okay, so once you're outside the shell, it has to be a uniform charge distribution. This behaves like a point charge. And that's the same with gravity. So for instance, the acceleration due to gravity on Earth is 9.8 meters per second square. So Earth is solid, but you could make it a shell and have denser material, and the gravity on the surface would be the same. Okay? All right. I'm going to now so this is just a point charge. I'll derive these two. Okay. This will be easy once you see this. Okay. So the electric field inside. Okay. So now we're going to find the electric field at this point. Okay, even though I didn't draw it symmetrically, so this is a symmetric shell. If at all there was an electric field, which direction do you think the electric field would be? So they're positive charges. Positive charges, the electric field would be in this direction. So if there is any electric field, it would be pointing toward the center. Okay, And for a given distance, the magnitude would be equal. Okay? So the flux for, so we're doing R less than R1. The flux would be E dot dA, and this is the okay, so this is the surface over which we're doing the surface integral. The area vector would be pointing out like that. Okay. And where do we have? So E is pointing in this direction, dA is pointing in that direction. That the angle between them is 180 degrees, so this would be equal to minus, and E is constant, it would come out minus dA, and just the sum of that area, which is 4 pi r squared. But that should equal the charge inside divided by epsilon naught. How much charge is inside this circle? There's no charge here. This guy is 0, so that guy has to be 0. So the electric field inside is 0. Okay? So just like that, if Earth were like this, okay, and you had a hollow interior, the gravitational field inside would be 0. And Mr. Newton proved that. That was a very smart thing to do. So if you had a basketball, and if you were inside a basketball, the gravitational field force of the basketball on you would be 0. Yeah. Now we're going to do part 2. We're going to find the electric field for somewhere there. Now this time, the electric field would be outward. And this is the Gaussian surface we would draw. Okay. So for this region, and I'm not going to draw the charge, and the area vector would be in that direction. Okay, the flux is, so what does the circle tell you? Very good. It's a surface integral over an enclosed area. If there's an electric field, its magnitude is constant. It's E times dA. So you're just summing over all those little areas. Yeah. And what is the surface area of a basketball? 4 pi r squared. Okay. So the flux is E times 4 pi r squared. And Mr. Gauss has told you, remember, that should be the charge inside divided by epsilon naught. What is the charge inside? It's all this charge. The total charge was Q, and it's uniformly distributed, so we'll calculate what is the charge here. Okay. The charge density is the total charge divided by the volume. What is the volume of this shell? What's the volume of the shell? What is the volume of a sphere? Go ahead. A volume, R cubed. Volume is length cubed. Okay, very good. Okay, so it's Q, the volume is the volume of this guy minus the volume of this guy. Okay, so 4 pi by 3 R2 cubed minus R1 cubed. That's the density. And so the charge inside here, this is R, is the density times the volume, this volume. Okay, so we'll call this QR. That's the charge inside radius R, is the density times that volume at radius R. Q over 4 pi by 3 R2 cube minus R1 cube, and that volume is 4 pi by 3 R cube minus R1 cube. This is the volume of the outer sphere, and this is the volume of the inner sphere. Okay. And of course, this cancels. Okay. So the charge QR, the charge inside radius R, is this. Well, how do we know if this expression is right? Let's make a check. If R goes to R2, what would be the total charge there? If R went to R2, that would be the total charge on that shell, which would be Q. So if R becomes R2, this cancels, charge will equal Q. Okay. So that's the charge inside. So what we have is, that's the charge inside. Okay. So E times 4 pi R square is that. So E times 4 pi R square equal to QR over epsilon naught. E is and again you see that this is behaving like a point charge, that is behaving like a point charge. Okay. 1 over 4 pi epsilon naught 1 over R square, and QR is R cubed minus R1 cubed divided by R2 cubed minus R1 cubed times Q. So that's the electric field for distances. It's a messy expression, but okay. And that's what this is. All right, again, what Gauss's law does is it allows you to calculate the electric field due to a symmetric charge distribution. That's what Gauss's law does. To remind you of the issue, again, let's say here is a point charge, here is a bunch of point charges. You want to find the electric field at this point. How do you find the electric field at that point? I'm sorry? So this guy will create an electric field like that. Very good. This guy will create an electric field like that. This guy will create an electric field like that. So to get electric field at that point, you have to add these three vectors. Well, you're not happy with that. You want the electric field here. Add 3 more vectors. Before long, you wouldn't be doing physics. Look, Mr. Gauss comes and shows you how to calculate the electric field at all these locations. Okay. He can only do that though when the charge is symmetrically distributed. Okay.
Is there like a natural phenomenon that has it symmetrically distributed?
The parallel plate capacitors I showed you, a lot of applications.
But that's a technology problem. So like, is there
Ah.
any nature?
Yeah, your bilipid layer in the cell. Mhm. So you can treat it as an electrical circuit. Okay. A long silver rod of radius 3 centimeters has a charge of minus 5 microns coulomb per centimeter on its surface. Okay, so how do I grab it and move it? Okay, so there's a silver rod, and you put minus 5 microcoulombs per centimeter. So if you throw a bunch of charge, where does the charge reside? On the surface. Yeah, this is a metal rod. So it'll reside on the surface. Okay. They say find the electric field at a point 5 centimeters from the center. Okay, so this is 3 centimeters, and they want you to find the electric field 5 centimeters from the surface. Okay. Now you should realize this. Once you're outside a symmetric distribution, this will act like the charge is right on the center. Okay. Once you're outside a spherically distributed charge, that charge acts like a point. So for instance, the space station going around the Earth, if you go home and suddenly flip a switch and make the Earth into a point object, turn it into a black hole, that orbit won't change. All those satellites would still be orbited. Nothing would happen to them.
So,
Mm-hmm.
what is the maximum distance you can go away from the surface while not treating it like a point charge? Like before you treat it like a point charge?
Once you're outside it, you're.
Just the
So find the electric field at this point. Now, we could use this formula, but I guess I'll derive it. This is the formula. You can look up your notes. Okay, but what I'll do is I'll just show you the derivation. So what we'll do is we'll draw a Gaussian surface, a cylinder of radius 5. Okay, outside. And the electric field, okay, so this is a negative charge, will be in this direction. Yeah. And we'll use Gauss's law. So Gauss's law says this integral okay, so that is the electric field, and the area is pointing in that direction. and the electric field is uniform. Oops. The electric field is uniform, so, and this area will not contribute because there the area vector is pointing like that, and the electric field here is pointing like this, so that surface won't contribute anything. Only this surface will contribute to this integral. Okay, so again, let me show you. So here's a sheet of paper. Here's the Gaussian surface, and the electric field is pointing into the sheet, perpendicular to the sheet. This surface doesn't contribute. So the flux is the electric field times this area. What is this area? What is this area? That's the side of a cylinder. And what is that? You cut a cylinder and it
Pi times height.
2 pi r times height. Yeah, all areas have length square. Okay, here's how you do it. You cut the cylinder, becomes a rectangle. That's 2 pi r. Okay.
See, that's why I said like that.
No, I knew I wasn't. Yep. All right. Okay, so you get a -1 electric field times 2 pi r times height. Okay, and that's equal to the charge inside divided by epsilon naught. So minus E well, what is the charge inside? They give you the linear charge density. 1 centimeter is that. Okay, so lambda, it's the linear charge density times the height. Linear charge density times the height gives you, divided by epsilon naught. The H cancels, so the electric field is minus 2 pi over epsilon naught lambda by r. All right, well, if this were 4 pi, then we could call it k, that thing. So all we do is we multiply the numerator by 2. So this is 2 over 4 pi epsilon naught. And 1 over 4 pi epsilon naught is k, the Coulomb's constant. So this is the electric field there. Okay, the negative sign because it was a negative charge and so on. Okay, so the electric field at a point outside is negative 2k lambda by r. So let's put in the numbers. Minus 2, k is 9 times 10 to the 9 Newton meter square Coulomb square, and lambda in our case was 5 microcoulombs, minus 5 10 to the minus 6 coulomb per centimeters, 10 minus 2 meters. And you are 5 centimeters away. You're finding the electric field 5 centimeters away from the center. Okay. As you can see, problems are getting a little more complicated in physics too. Okay. The negative sign cancels, this 5 cancels, that becomes 10 minus 4 and 10 to the 5. So the electric field is 10 to the 5 Newton per Coulomb. And then what you left is 2 times 9, 18. Okay, so 18. Does this electric field ring a bell? Okay.
Not sure what though. But it does.
All right. What do you need to have a spark in air?
3.
Very good. 3 times 10 to the power 6 Newton per Coulomb. Okay, so the electric field is a little less than that. So maybe if you get closer to the rod, maybe the electric field will be strong enough where you'll have sparks flying. Okay.
Does it depend on the material of the rod that changes the field?
All you need is electric field. So what does the electric field, strong electric field do? Any stray electrons in the atmosphere will start knocking off electrons from the molecules in the atmosphere. Okay, I'll do 2 more problems because most of you guys are, Christina here is falling asleep. So. I'm just picking on you because you're easy to pick on.
Oh, okay.
And Nolan doesn't mind. He agrees. All right. 2 parallel conducting plates. Okay, again, this is a parallel plate capacitor. Each of cross-sectional area 400 centimeters square. 400 centimeters square is roughly 3 pages. Okay, so take 3 pages. No, not quite 3 pages. Okay. Maybe 1 page. 8 inches by 8 by 11 inches. 8 inches is 20 centimeters by 30 centimeters. That's 600. Less than a sheet. Okay. Are 2 centimeters apart. So here you've taken 2 sheets. And they're this far apart. Okay? And if you charge them, what have you done if you charge these 2 plates? If you charge them, you've stored energy. Okay? 2 parallel conducting plates, each of cross-sectional area are 2 centimeters apart and uncharged. So when they're uncharged, how much energy have you stored? 0. If trillion electrons are transferred from one plate to the other. So you take electrons from here and put them there. This guy becomes positively charged, and this guy becomes negatively charged. This is Q minus Q. And they want you to find the charge density. What is the charge? Is N, the trillion electrons you took, times the charge of an electron. Okay? And the charge density on the plate is, okay, charge divided by the area. What happened? I hit something accidentally, didn't I? All right, so the charge density is that. Okay, so this is equal to the N is a trillion. What is the charge of an electron? 1.6 times 10 to the minus 19 Coulomb. Okay, say that 100 times. All right. Area is 400 centimeters square. Okay. So sigma is, okay, that's 10 to the minus 15. That makes it 10 to the minus 3. 1.6 divided by 400. Coulomb per meter squared. All right. And they want you to find the electric field between the plates. For the parallel plate capacitor, you saw that the electric field is sigma by epsilon naught. And this electric field okay, not quite enough to cause a spark. Okay. So here's the deal. Now you've learned something. In a parallel plate capacitor, you're storing energy, and the more charge you put, the more energy you store. Can you store an infinite amount of energy? No. You saw that as the electric field gets stronger, after a point, when the electric field gets to be 3 million volt per meter or 3 million Newton per coulomb, sparks will start flying. And this will discharge like, you know. And so there's a maximum amount of energy you can store in a capacitor. Okay. All right, we'll do one more problem. What is a vector field?
XYZ.
You're associating a vector with every point. Okay, so that's a vector field. Okay, and so you see, at every location, the vector is pointing in the z direction. And so this vector field depends only on x. And as you go further and further, what is happening to the vector field? It's becoming bigger and bigger. What is the vector field at this point? Again. Okay. So it's not a function of y and z, it's only a function of x. Okay, so that's how that vector field looks like. Calculate E dot n dA, where S is the area shown. Okay, so they want you to calculate the flux through this. Okay, so the flux is E dot. Okay, why don't we have a circle on that integral? Very good. Okay. And the area is, we'll say dx dy. So this is 3x squared k dot dx dy k. That's the area. Okay, this n equal to k. Okay, so that's that area. K dot k is 1. And y dx goes from 0 to a, and y goes from 0 to a. So you got y x cubed, 0 to a, 0 to a. So a from the y and times a cubed. So that's what you get for the flux.